In this fourth and final segment of thermochemistry, we're going to talk about Hess's law. Now, Hess's law states that the specific path leading to the formation of different B products from A reactants does not influence the overall enthalpy change. If you look, we could go a direct route from A to B just using delta H1. But if we took delta H2 and delta H3, we would end up in the same place. Also, if we took delta H4, delta H5, and delta H6, we would also end up in the exact same place. This is equivalent to you going to the restroom and taking the direct path or taking a lap around the school and going to the same restroom. You always end up in the same place. The reason we use Hess's law is because some chemical reactions are hard to find their delta H, but we can use similar chemical reactions and add them together in order to get the delta H for that specific chemical reaction. When using Hess's law, we have to follow three rules. Number one, when adding two or more reactions together, their delta H reaction values should also be added together. Number two, reversing the direction of a chemical reaction reverses the sign of the enthalpy change but does not affect its magnitude. And number three, if we multiply all components of a chemical reaction by some number, the enthalpy change should be multiplied by the same number. In order to show all three of these rules, we're going to do a Hess's law example. This one asks, what is the delta H for the following reaction? So let's look what we got. First of all, this might be an equation that's really hard to determine its delta H, but we have three reactions that we can add together in order to get the enthalpy change. So let's go through this together and see how we are going to deal with these three reactions and come up with the reaction that we see in red here. The first reaction, if I look at it, has CS2 on the right side as a product, but we need to make sure it's as a reactant in our final equation. So we're going to have to reverse that reaction. So when I reverse that reaction, as we see here, look what happens to the sign of delta H. We changed it from positive 87.9 to negative 87.9. In the second reaction, CO2, which is the product side in the original reaction, is also on the product side in the final reaction. It also has a coefficient of 1 in both reactions, so we're not going to do anything with that. We're going to keep the second reaction exactly the same, which means that its delta H stays exactly the same. Now, if we look at the third reaction, SO2 is a product in both reactions, so we're not going to reverse the reaction. But in the final reaction, or the reaction in red, it has a coefficient of 2, and the equation that we're using up in the box up there on the right only has a coefficient of 1. So we're going to have to multiply all of the coefficients by 2 in order for us to have 2 SO2. So let's double that third reaction. Notice that when we double all the coefficients, the delta H of the reaction of the original equation must also be doubled. Now that we have all three reactions where they need to be, let's cross off the things that cancel out. You'll notice that the carbon is on the right side of the first reaction, but on the left side of the second reaction, so it cancels out. You'll also notice that there are 2 sulfurs on the right side of the first reaction and 2 sulfurs on the left side of the third reaction. They will also cancel out. What we look at now is the red numbers, and we add them together. So we have 1 CS2 in the first reaction. We have 1 O2 in the second and 2 O2s in the third, giving us 3 O2s. Notice that matches the final equation at the top. We have 1 CO2 as a product, and we have 2 SO2s as a product as well. So the final reaction that we have is equal to the 3 reactions added together. So in order to do that, we also add their delta H of reactions. If you look at it, the first reaction was negative 87.9 because we had to reverse the sign. The second reaction stayed the same at negative 393.5. And the third reaction, we had to multiply negative 296.8 times 2, which gave us that negative 593.6 kilojoules. When we add all three of these together, We end up getting a delta H for the reaction of negative 1075 kilojoules. That is the same as if we would have done the CS2 plus 3O2 yields CO2 plus 2SO2. Notice we used 3 reactions to get the same enthalpy change as if we would have done that one reaction.